done a lot of the introduction for me, so I can go quite quickly through that. Just to remind you, we have individual atoms. These are identical atomic qubits, each held in their own optical tweezer, done in a way that scales easily to hundreds, if not thousands of atoms. We can code qubits in long-lived hyperfine mononuclear spin states, in states that basically do not interact with one another. But we can also realize strong and coherent interactions by exciting these high-line states. Right, and so this is our natural tool for realizing many-body physics, but also for two-qubit gates, where we're also seeing really impressive progress. So just to highlight, even in the last year or so, all the progress that has been made, it's clear that there's a lot of excitement for this platform, and it's a really fun time to be working on it. But like every platform, of course, we have challenges, and two that stand out in particular are that measurements are typically quite long, they're destructive, and they're not qubit specific. And as Julia just mentioned, we always have to contend with atom loss. So as you run deeper and deeper circuits, you are going to lose atoms, and at some point you just run out of atoms. And so this really brings us to the question, why would you want to build a dual species array? And Julia's just done a really nice motivation of that for me. But this is my take on it. Well, first, we have potential solutions to these challenges. So we have distinct optical transitions for each species. And that means that, for example, we can image one species without disturbing the other. Okay. And moreover, the cooling transitions that we use are also party tuned. And the traps that we use are also wavelength dependent for each species. So we can make our traps selective. And this means that we can think about doing things like reloading one species of atom whilst preserving coherence on the other, such that we always have a supply of atoms. On top of these solutions, there are also opportunities. And we heard a bit about the new interaction regimes we can access, and later in my talk I'll expand on that a little bit. We have efficient multi-qubit control, because again, each species has its own addressing transitions, and putting everything together leads, for example, to these auxiliary qubit-enabled protocols. So what I'll do in my talk, it's a short talk, but I'm going to crash through the state of our experiment and just highlight one recent result. And then I'll spend the second half talking about what we're doing right now. This is very much a work in progress, but adding interactions into the system and where this might go with quantum simulation. So our experiment looks much like the others you've seen, with one little distinction, that we have two SLMs here, which generate two independent trapping arrays, one for rubidium and one for cesium. And each of these is at its own wavelength. And what that means is that when we want to trap rubidium atoms, they only get trapped in the rubidium traps. And when we want to trap cesium atoms, they only get trapped in the cesium traps. We load our atoms stochastically, but we share one set of cross-diffuser optic deflectors that can actually rearrange both types, and this is how we can make defect-free arrays in 2D. And so here's an example of the largest system that we've demonstrated so far. So this is 512 trapping sites, where in yellow you see cesium atoms and blue rubidium atoms. For the experts, this is average fluorescence, but we can make this defect-free. So I said I want to highlight one key result, and that's really showing that we can do these mid-circuit measurements in our system. And so the protocol we decided to demonstrate this with is called a spectator qubit protocol. So I want to walk you through that first, just to give you a flavor of what's going on. So we have an ensemble of data qubits, and we can represent them on the XY plane of the plot sphere like so. And what's happening is that each time we run the experiment, those qubits are interacting with a noise field. And so in each shot, they gain a different phase. We average over the shots. What do we get? Decoherence. Of course, that's something we want to overcome. And a really interesting scenario comes up if you have a second set of qubits that also feel the same noise field and thus undergo some sort of correlated dynamics. Because it turns out that with a single mid-circuit measurement on that ensemble of spectators, you can actually estimate this phase by measuring, for example, along the y-axis, figure out what that would mean for the data qubits, and correct it in real time. So this is a protocol that's targeted specifically at correlated noise, which is maybe a little bit of a special case. Of course, you could combine this with whatever quantum error correction you like, but I also want to point out that not everything wants for quantum error correction, and especially for things like metrology, this could actually be really powerful. A really nice feature of this protocol is that it doesn't need 2 qubit gates, and that was really handy because at the time we didn't have any. But it does have some kind of strict requirements. So you have to do mid-circuit readout on the spectators without decohering the data qubits. The measurements have to be fast compared to the coherence times in the system. And in this case, everything is done in real time. So we have to process the data, so get images off the camera, calculate all our corrections, and apply that on the experimental runtime. And so I want to cut to the chase and just show kind of the main experimental result. There's a lot more to say here, and I'm very happy to discuss that later. But the key result is this. So we took our data qubits, they're undergoing some planar coupling, and they're exposed to some magnetic field noise. In each run of the experiment, that noise has a completely random phase, that's unknown to us. And what you see is that when you average over all the data, well, what happens? Those data qubits decohere. But then we can run the full protocol, and we really run this, we turn it on in real time and just see what comes out. And when we do that, we get the following. So we can actually recover the coherence, we can correct this noise in real time. And so that's the key message. Actually already in this platform, we can do mid-circuit measurements, we have long coherence times, and robust high qubits. But as I said, up to this point, we had no interactions, and so I'm now going to switch gears a bit and tell you where we're headed and what we're currently trying to do in the lab. So, Julia talked a little bit about the different interaction regimes we can get for inter- and intra-species, and how this tuning can be powerful. And I just want to elaborate on that a bit. So, we can talk about exciting cesium and rubidium atoms to high-line Rydberg states. And we can first start with the case that both of them go to the same end state. And in this scenario, I'm going to be talking about S states. And so in this scenario, we get strong van der Waals interactions. So we scale this n to the 11 over r to the 6. And this gives us our gigahertz interaction over several microns. We can look at a specific case. So this is for 68s half rubidium, 68s half cesium. And what we see is that in all 3 cases, so our cesium, cesium, rubidium, rubidium, and rubidium cesium interactions, they're all doing more or less the same thing, right? So we get this 1 over r to the 6 slope. You have this slight hierarchy of energies, but they're all pretty similar. Now, an interesting thing happens for dual species experiments, though, because you can get what's called a Forster resonance. And so this is a very specific case where if we now look at our eigenspectrum of Rydberg pair states, the energies come close together. And now instead of having this second order dipole-dipole interaction, we come back to a resonant point. And so this is similar to physics to what Daniel talked about, but this actually occurs directly out of exciting to these S states. So by changing cesium by just 1 n, bringing it down to 67, what you see is we get completely qualitatively different behavior. So we can turn on this Forster resonance, and now we get an interspecies interaction that scales as n to the 4 over r cubed. And this really gives us a new tool because we can actually engineer different asymmetries of interactions in this system, such that now, for example, we can have cesium, cesium, and rubidium, rubidium comparable, and more than an order of magnitude asymmetry to our rubidium cesium. And so this is something we're really excited about, especially for quantum simulation, realizing what scenarios we can access. So I want to flash some really preliminary data. Since about March, we've been trying to add Rydberg excitation into our system. And so what I'm going to show you is that we can take our cesium atoms, we can drive ground Rydberg transitions here, we can take our rubidium atoms, we can also drive ground Rydberg transitions here, and then we can pair up our atoms so we can bring them close together. Because these are distinct species, we have efficient control, so we can just apply a pi pulse to our cesium atoms, and then we can try and drive Rabi oscillations on our rubidium atoms. And when we do that, our oscillations disappear. right? So this is really clear evidence of strong Rydberg blockade for the first time between atoms of different elements. And so this is really the building block that we need now to start implementing gates and also interactions with quantum simulation. And so that's what we're working on right now, is demonstrating our first gates, and hopefully we'll have results to share that before too long. So in the last couple of minutes, I just want to talk about where we're headed with this, more on a point of quantum simulation. And I actually want to take a step back and to start with just the single species transverse realizing model. So this is, I think, really was the workhorse Hamiltonian when this system started. And it's just comprised of basically three terms. You have a Rabi frequency that's global on all your atoms, some detuning, so these are things we do with our lasers, and then our Rydberg interactions. And so it was shown, for example, in this 2017 work, that you can tune your 1D system across into these different phases where you can see Z2, Z3, Z4 bullets, etc. And then from exactly this Hamiltonian, a lot of really rich physics followed. So we had a little bit about the idea of many body scars, which were discovered for the first time in this system. There was work done on the quantum Kibble zero mechanism. Then the experiments upgraded. They went beyond 1D into 2D, and suddenly we saw phases and phase transitions in 2D, so the square and triangle lattices, as Daniel talked about. And then, of course, also this beautiful spin liquid work on the Kagome lattice. So what this serves to say is that even with those tuning knobs and this programmable geometry that comes so naturally to us, there's already so much physics. And so I can make a more complicated Hamiltonian with even more tuning knobs. And so these are things that we can control with lasers, so different Rabi frequencies for each species and detunings. And we also have this ability to set different interaction strengths that arise both from our choice of Rydberg states and geometries, such that we can tune, for example, our cesium-cesium, rubidium-rubidium, and rubidium-cesium interactions. And so even in 1D, the phase diagram of this system, to our knowledge, is completely unexplored. And so we're starting to think about this, working a little bit with Natalia Chepiga at Delft, and I think this will be a natural place to start. But as Julia also said, there are lots of other things that come. So we actually picked the same reference, it seems, where there's this really nice lattice gauge proposal that was actually first proposed for a single species experiment. And the idea was that actually you would have two 2D systems where one set of atoms is kind of lifted out of the plane. Now, an experiment, that's quite difficult. I mean, 3D experiments have been done, but there are challenges. Here we can actually replace this 3D system just by tuning the interaction strengths, right? So we take a 2D system and we can make it quasi 3D. We have this species selective control, and that gives us efficient ways to prepare initial states in a way that is also often challenging in single species experiments. So we can think about adding impurities or dopants into systems, and we can also add dissipation on sites of our choice. And then finally, of course, we can add these longer range and flip-flop interactions via booster resonances. Of course, we're thinking about lots of other things on a slightly more quantum information vein. We have really nice protocols, I think, for making large 2D cluster states through mediated gates. Of course, quantum error correction ties naturally to this idea of conserving measurements, and that's something we're really keen to explore. Putting some of these things together, there are ideas for quantum advantage through shallow circuit sampling, particularly tying back to the 2D cluster states. And then just to say, we're really happy to take ideas. So if you'd like to chat, please reach out to me or to anyone else in the group. Send Hannah's an email, and that would be great. So I just want to wrap up. Thank you for listening. I really encourage you to see Bob's poster on Thursday, where he will tell you a bit about our Generation 2 experiment. So we're building another dual species array. I can tell you about more of the experimental details, but also the upgrades that are planned there. And of course, to thank the team, so Hannes and particularly Kevin, Shraddha, Ryan, and Vikram, who worked with me on the dual species set. And I'm very happy to take questions.
Hi, thanks for the great talk. I had a quick question at the beginning on the world wave mirrors.
Yeah.
Yes, I'm just curious about what percentage of the errors you expect to be correlated versus uncorrelated.
I think this really depends on the architecture and the type of errors. So the case we were looking at here was magnetic field noise, and to be very clear, we worked here in a regime where we could control that noise. So we actually first had to bring the noise level down because it was too bad to start with, but then we actually experimentally brought it low enough to be able to do things in a controlled way. Generally, there are many sources of correlated error within these platforms. So, for example, laser intensity noise. A lot of these things are done with global beams, and then that is something that naturally occurs. Electric fields and magnetic fields are nearly always correlated, right? These are not random things. We don't really worry about things like cosmic rays, but more local things.
Cesium oscillations, like radio oscillations, worse in the way of movement.
Yeah, lots of technical noise. So, to be clear, building this is full counter propagation lasers that have to be locked extremely well. So we have to have extremely low phase noise. Actually, having said that, the majority of the amplitude here comes from STAN. So the other thing is that this is all done on the hyperline block qubits, and right now the way we prepare those qubits, the experts is bipolarized state pumping, which is not the most friendly way to prepare such states. We're currently actually building up Raman lasers that should basically remove the vast bulk of these errors.
If there are no final questions, then I think we can wrap up. Then we'll be back